Standard machine learning regression algorithms have a greed problem. If you tell them to minimize their error on a set of training data, they will do whatever it takes to achieve a perfect score. The algorithm will stop looking for the actual underlying pattern and start memorizing random background noise instead. This is called overfitting. This scatter plot shows a healthy model's smooth line. Run unchecked, it turns chaotic, spiking to hit every dot. Next to it, a bar chart tracks internal weights. To make these spikes, the algorithm forces its coefficients to grow massively, pushing right off the scale. This model might ace its practice test, but because it memorized the noise, it will fail the moment it encounters new data in the real world. To stop the weights from spiraling out of control, we use a technique called regularization. It adds a mathematical penalty to the algorithm's loss function, acting like a chain that restricts how large those weights can grow. When you open a machine learning library, you typically have three options for this penalty: Ridge, Lasso, and ElasticNet. On paper, the formulas for Ridge and Lasso look dangerously similar. The only difference is the penalty term at the end. Ridge uses a squared coefficient, while Lasso uses an absolute value. Guessing between them is a risk. Pick the wrong one, and your model might arbitrarily delete critical data, or it could get bogged down processing useless variables. To stop guessing and deploy the correct tool, we have to look past the algebra and understand the distinct geometric shapes these penalties create behind the scenes. Ridge regularization, also known as L2, penalizes the sum of the squared coefficients. Ridge's squared penalty scales downward force with weight size. Massive weights shrink rapidly, but as they near zero, the force weakens, never reaching absolute zero. Graphically, this forms a circular boundary. Expanding error rings hit the circle at a tangent, leaving both variables active. This gives Ridge a unique mathematical capability. It allows you to solve equations even when you have far more features than data points, like analyzing 10,000 gene expressions using a sample of only 500 patients. Ridge acts as a smoother. It creates a dense, stable model that utilizes every single piece of data you give it, maximizing predictive accuracy at the cost of being heavy and hard to interpret. Lasso regularization, or L1, takes a different approach. It penalizes the sum of the absolute values of the coefficients. Lasso applies a fixed, unyielding downward force regardless of weight size, driving irrelevant weights straight to absolute zero. On a 2D plot, its absolute formula draws a sharp diamond. Expanding error rings strike the diamond's corner on the axes, forcing one variable to zero. Lasso acts as an executioner. It performs automatic feature selection, killing off useless noise, like the color of a house when predicting its price. You get a sparse, lightweight, and easily readable model. Lasso has a blind spot when it encounters highly correlated features, like having both house size and number of rooms in the same dataset. When faced with both, Lasso will arbitrarily select one feature and ruthlessly force the other to zero, wiping out valuable contextual data. ElasticNet regularization solves this by combining the absolute penalty of Lasso and the squared penalty of Ridge into a single loss function. It balances the two forces. It retains Lasso's ability to kill off completely useless features, but applies Ridge's smoothing effect to shrink correlated features together, preventing either one from being arbitrarily dropped. ElasticNet delivers the ultimate compromise, solving the correlated data trap to keep the model both stable and rigorously filtered. To dictate how severe these penalties should be, you have to tune manual dials called hyperparameters, usually labeled as lambda or alpha. For Ridge and Lasso, you only have to tune a single dial through cross-validation. This is computationally cheap. ElasticNet comes with a hidden cost. You have to tune two separate dials, one for the overall penalty strength and another for the ratio between the L1 and L2 forces. Looking at this quadrant chart comparing computational cost and model stability, ElasticNet sits perfectly in the top right corner. Tuning two parameters creates an exponentially larger grid search, significantly increasing the required compute time and processing budget. Because of this massive compute cost, ElasticNet should be reserved for datasets where correlation is a known problem, rather than used as a lazy default. There is no universal best choice among the three. The algorithm you select dictates the core architecture of your final model. This flowchart maps out the decision. If you have to explain exactly which variables drove a decision to a stakeholder, choose Lasso for a sparse, readable model. If raw predictive accuracy on unseen data is paramount and model weight isn't an issue, Choose Rich to retain every nuance in the data. And if your dataset is highly correlated and you have the server budget to tune multiple hyperparameters, deploy ElasticNet. By understanding the geometric difference between a circle and a diamond, regularization goes from a black box guessing game to a deliberate strategic engineering choice.